Hello everyone, and welcome to the sixth part of Seismic Analysis with IS1893. I am Surajit Ghosh, and in this video, I will discuss about ST parameter in STAAD, how time period of different structure is calculated following the guidelines of clause 7.6.2 and its impact on seismic analysis. Time period and structural behavior of a building with and without infill wall is different. How we can consider this additional stiffness of wall during seismic analysis? That I will cover in detail. In last session, I have discussed about 5 basic parameters which are required for AH and design base shear calculation, including Z, I, RF, SS and DM. Last two parameters, soil class and damping ratio, is used for SA/G calculation. If we look at figure 2 or equations mentioned under clause 6.4.2, we can notice that SA/G depends on the soil class and damping. By default, 5% damping is considered, and for any other damping ratio, SA/G is multiplied with a factor. There is another input on basis of which SA/G is determined, the fundamental natural period of the structure. In part 3, we have a detailed discussion on this topic, how earthquake ground acceleration data is simulated on different SDOF system with different time period, and maximum normalized response is recorded in this design spectra curve. We can use this to find out the design acceleration coefficient using the exact time period of that structure. As the slope of the curve changes drastically in few regions, it is very important to calculate the natural period accurately, else incorrect seismic force will be considered for design. For example, if the time period of a structure is 0.5 second, then for medium soil, SA/G is 2.5. If the time period is considered as 0.8 by mistake, then SA/G is calculated as 1.36 by 0.8 or 1.7. which is only 68% of the actual SA/G value. So we are considering 32% lesser lateral force for design, which might be fatal for the safety of the overall structure. That's why accurate calculation of time period is important for proper seismic analysis and member design. Time period is basically the time required to complete one full cycle of an oscillating SDOF system, and it depends on several factors, including stiffness and alignment of the lateral framing system. You can go through part 3 for a detailed discussion on this topic. Just for an example, consider these 3 scenarios. First model is a simple concrete structure with bidirectional lateral framing system. In the second model, sections are modified to steel. Rest of the inputs are same. In the final model, few shear walls are modeled in both X and Z direction. For each model, I have extracted the natural frequency and time period of the first 6 modes. If we compare it from the output file, we can easily notice that there is a difference between all these values. This suggests that depending on different structural condition and stiffness, natural period of the structure is modified. More steep structure displays less and has a lower time period, whereas ductile structure takes more time to complete a single cycle, hence higher natural period. For this example, I have used modal extraction method. It is a bit complex, and for static seismic analysis, eigensolution is not used for time period calculation. Rather, could suggest few empirical equations under clause 7.6.2 based on different structural condition, and we need to follow this to compute the fundamental natural period of the structure. This is a simple and conservative approach to calculate an approximate time period, most of the time which is lesser than the actual time period of the structure. So higher seismic force is considered for analysis. Smaller time period means higher seismic force, right? There are 5 different equations. First 3 are used for moment resisting frame without any wall, and last two are used for any structure with RC or URM infill wall. If there is no reinforced structural wall present in the model, and if the masonry walls are not modeled or considered for analysis, then depending on the material used in the model, three separate equations are provided. One for pure concrete structure, one for pure steel structure, and another one for mixed type of structure with both concrete and steel sections. These five equations are considered in STAAD for static seismic analysis using structure type or ST parameter. Each equation is marked with a number starting with 1 for RC-MRF building and ending with 5 for all other building. When a value of ST parameter is defined, corresponding equation is used for natural period calculation. For example, ST1 means first equation is used. ST4 means equation for RC wall is used for fundamental period calculation. This parameter must be defined properly depending on the type of structure, else time period and corresponding SA by G value will be calculated incorrectly. Let's check how we can define this ST parameter for different type of model. For this structure, no RC or brick wall is modeled. Concrete beam and columns are used in both directions to resist the lateral force. Hence, we can consider it as a concrete MRF building and define the ST parameter as 1. In this PEB structure, only steel sections are used. I have modeled the rafter and column using tapered plate girder section. Angle sections are used for bracing, and channels are used as purlin and girth. I have used this model in the series on modeling, analysis and design of PEB structure. You can check this from my YouTube channel. For this model, we need to define the value of ST parameter as 3. Final model. It is a composite MRF building. Concrete sections are used as beam and column. Few steel columns are used along with a steel truss at the roof. For this type of structure, ST should be defined as 2 to consider RC steel composite building equation. When both concrete and steel sections are used in the lateral framing system, we need to use this equation. One thing you can notice from these equations, when the stiffness is changed with material from concrete to steel, time period is increased, which is quite normal. Though these models are different, there is one similarity. No walls are modeled for any of this structure. For any high-rise building, it is quite common and also required to include several shear walls in different location and direction. When you introduce a shear wall, load transfer path and structural resistance to lateral force is modified. So, time period of any concrete building with a shear wall should be different from a bare MRF building. That's why couple of equations are provided for buildings with RC and URM infill wall. We can define these conditions using ST4 and 5 parameter, but there are few additional inputs. Also, it is quite common to have two different framing systems in different direction. How we can handle this in STAAD? That I will cover in the next part. Stay tuned.